Welcome back, everyone. This is Professor Herring. In this video, we're going to learn about solutions. We're going to talk about what the components of a solution are, the different types of intermolecular forces that are formed and broken when a solute dissolves in a solvent. We're going to specify the factors that can make dissolution occur spontaneously, and then we're going to end by learning about strong, weak, and non-electrolytes. Now, you might have heard the saying, if you're not part of the solution, you're part of the problem. However, because this is chemistry and we like to make silly jokes, we're going to change this to, if you're not part of the solution, you're part of the precipitate. Now, if you thought that it couldn't get any nerdier, then I actually own this shirt. And one day, if you're on campus and you see me, well, let me know in advance that you're coming, and I'll try and bring my shirt and wear it for you. All right, let's begin. So, what is a solution? A solution is a homogeneous mixture. And this is in opposition to a heterogeneous mixture. And that's missing an E. And a heterogeneous mixture is one that is different throughout. So imagine that you have a bucket. And in the bucket, you've got, these small balls or whatever here on the bottom. And then you've got a big piece of paper and a rock. This is a heterogeneous mixture because it's different throughout. It's not uniform. A homogeneous mixture is one that is uniform and has the same properties throughout. So it doesn't matter if you scoop from the middle of the bucket or the bottom of the bucket or the top of the bucket, you'll get the same stuff. The solute in a solution is the minor component, the smaller amount, whereas the solvent is the major component, typically has the larger mass or larger volume. And an aqueous solution is specifically a solution in which water is the solvent. So we can get other types of solutions, ones that are not aqueous. And we've seen already in Chapter 12, we learned about mixtures of gases. We learned about how the atmosphere is a combination of nitrogen, oxygen, argon, helium, neon, etc. And that makes up the solution of air. However, if you take and put gas and liquid, as in a carbonated beverage, you can get a solution. If you put liquids together, such as alcoholic beverages, that's a solution. If you put solids into liquids, like sugar water, your Kool-Aid or whatnot, that's a solution. And then we can get to some ones that are maybe a little bit less familiar. A solid solvent with a gas solute, that might be hydrogen gas absorbed by palladium metal, and that occurs in various types of fuel components. Okay, if you put liquid into solid, that's what happens in your mercury that gets put into silver fillings. That's not done so much anymore, but that's an example of one that used to be more common. And then finally, steel alloys are an example of solids mixed with solids. So you can get iron and carbon that are mixed together, both of them being solid, and that's going to get you a steel alloy. And alloys are examples of solutions. So what happens on the molecular level when we dissolve stuff? So let's take an example of salt and water and sugar and water. And so we can look at before and after. Before, we're going to have these water molecules, and I'm going to approximate them as this. Okay? And so we'll have these water molecules that are surrounding this giant cube. And what happens is the water molecules, they break apart. They do two things. They dissociate the ions from each other, and they dissolve them. And this is surrounding them. And so what we see here is that the sodium and the chloride are dissociated from each other. They're broken apart, and they are also surrounded by the water molecules. They're dissolved, or solvated is another term. If you look at sugar and water, you're going to have these sugar molecules, and they don't dissociate. Sugar molecules stay together. However, they do get surrounded by the water molecules and therefore are dissolved. And there's a really cool simulator that you can see online. I recommend that you go check it out. This is the same website that you might have seen when looking at the molecular shape simulations. And so we see that there are some differences in the dissolution process. Now, what gives rise to those? Well, it turns out that the types of bonding that occurs within the solute makes a difference. What we see here with salt and water, this is an ionic bond. And ionic bonds are going to break apart in the water, whereas these are all covalent bonds. And the covalent bonds, it turns out that they don't. So even though we've talked about before that ionic bonds are stronger than covalent bonds, it turns out that those ionic bonds will break in the presence of excess water, whereas the covalent bonds do not. So let's talk about what's going on step by step here. What we want to do is focus on the energy changes that are associated with dissolution. So we first will have a solvent and a solute that are not mixed together. And what you do, one thing that happens is that we break the solute interactions. Because breaking interactions requires energy, we see that this is going to be endothermic. We also need to break the solvent-solvent interactions, and that requires energy. Finally, when we form the solvent-solute interactions, that releases energy. And so the enthalpy of the solution is the sum of all of those different steps. Now, it doesn't really matter if we were to depict the breaking of the solute before the solvent. In reality, it's all happening simultaneously. But when we look at it this way in a stepwise fashion, it's a little bit easier to understand what's going on. So what dictates what things are going to dissolve together? To understand this, we want to apply what's called the like-dissolves-like principle. This is where substances with similar intermolecular forces will mix well. In other words, they'll be soluble together. An example of this is polar molecules with salts. Salts are examples of ionic compounds. You can also mix nonpolar and nonpolar compounds. And substances that mix in any proportion are called miscible. So these are examples of scenarios where you're going to dissolve, but things that don't dissolve are things that are really not the same. So if you have a nonpolar with a polar molecule, or a nonpolar with ionic molecules, ionic compounds, these don't end up mixing well together. And we know, however, that there's a spectrum, right? You can have, if we're looking at organic compounds, we can have methanol versus ethanol versus propanol, and this is an order of decreasing polarity overall. However, all of these still have a region that is polar, and so you're going to see that while we use this rule like dissolves like, it's a little bit more nuanced, more complicated, and so we usually talk more about ranking things by their solubility. We already looked at this a little bit, but so it's important to realize that when water dissolves ions, it forms a sphere around those ions. And we call this a solvation sphere. This leads to the dissolution of our salt. So for the example of sodium chloride and water, we break the ionic interactions between the sodium and chloride ions. We also break the hydrogen bonds and the dipole-dipole interactions and the London dispersion forces within water. And then we form the sodium water and the chloride water ion dipole interactions. And these are the steps that occur in the solution process for water, or for salt in water. It's important to realize that the solvation process is reversible. So if we evaporate the solvent, we're going to recover the solute in a pure, unchanged form. This means then that the solvation process is not a chemical reaction. So for example, we could take solid sodium chloride, add water to it, and it would dissolve and become aqueous sodium ions and chloride ions. However, if we dissolve iron in hydrochloric acid, that's going to produce iron chloride and hydrogen gas. In both of these cases, we're going to end up with a liquid, which is mostly water and has some of these ions floating around in it. But if we evaporate off the water, in the case of sodium chloride, we get back the sodium chloride. And so we have reversed the entire cycle. However, if we evaporate off the water in our iron mixture, we're going to produce iron chloride, which is not the same thing that we started with. Therefore, the second is a chemical reaction and the first is not. So when we look at the solvation process, we need to recognize that we can have both endothermic and exothermic type reactions. When we looked at the case of sodium chloride, that was an exothermic reaction, where the sum of the enthalpies added together is negative. However, we can get cases where, due to the strong intermolecular forces between either the solvent and solvent or the solute and solute, that it requires more energy as a total than is given off. And in this case, we need a different driving force. When the solution process is exothermic, that gives off energy, and that release of energy lowers the energy of the system and makes it more stable. But what happens in an endothermic process? Endothermic processes occur because enthalpy is only one part of the picture. Processes can occur spontaneously when the energy is released, and also when disorder or entropy increases. So we've talked already about gases, and if we talk about two gases that are diffusing together, then initially there is higher order because they're uniform throughout. However, when we open up the hole and we allow them to mix, they're going to have higher disorder, and that is favorable. That occurs spontaneously. An example of this would be if we have carbon tetrachloride and hexane. And when they mix together, that's going to lead to an increase in disorder. And these two processes are linked to each other. A process can be endothermic if there is an increase in entropy or disorder that is large enough. We're not going to go into details and quantify entropy at this point in Chem 110, but we do want to point it out to you. You'll learn in Chem 112 more about entropy and how to calculate the entropy of a reaction and use that to determine whether or not a reaction is going to be spontaneous. Let's now turn our time to electrolytes. Electrolytes are substances that dissociate into ions when dissolved in water, and they conduct electricity. We have three types of electrolytes: strong, weak, and non-electrolytes. Strong electrolytes are going to dissociate 100% in water. And remember what we talked about, the difference between dissolving and dissociating. Dissociate means that they're going to break apart into ions. And there's three classes of compounds that are going to do this. The first is salts, which are ionic compounds. And we already have talked about ionic compounds consisting of metals bound to nonmetals. The exception to that being the ammonium ion. There are also strong bases and strong acids. We're not going to go into great depth about acids and bases other than understanding that bases are able to give off hydroxide, whereas acids give off H plus ions or protons. There's a list on the ebook with 7 strong acids and 8 strong bases that you need to have memorized. See lesson 2 of chapter 14 for that list. Then we have weak electrolytes. These are substances that dissociate only to a limited extent. These are weak acids and weak bases. And essentially, if it's an acid or a base, but not on the list of strong acids or bases, then it's going to be a weak electrolyte. The third group is non-electrolytes. And non-electrolytes don't dissociate at all. And this is essentially everything else. Let's review a little bit to remind ourselves what the dissociation process versus dissolution process looks like. Remember, with salt and water, we have both dissociation, which is where it's breaking apart into ions, and dissolution, where it's surrounded by the solvent. In the case of covalently bound compounds that are not acids or bases, such as sugar, those are going to dissolve but not dissociate. So let's talk a little bit about identifying acids, bases, and non-electrolytes. For acids and bases, there are 2 categories for each. For acids, those are compounds when to recognize them, look for a molecular formula that starts with H and then is followed by something else. For example, we have HF, HI, H2SO4. And for those types of acids, some of them will be strong and some of them will be weak. Then we have the functional group, carboxylic acid. As the name implies, these are acids. And these are always, for our cases, going to be weak acids. For bases, we have metals bound to hydroxides. Some are strong, some are weak. You need to know the list of strong bases. And then finally, we have our functional group, which are the amines, which are nitrogen-bearing compounds. And for the non-electrolytes, all other functional groups, alcohols, esters, amides, ketones, ethers, etc. Those are all going to be non-electrolytes. There's a flowchart in the ebook that I recommend that you become familiar with that walks you through determining whether or not a substance is going to be a strong, weak, or non-electrolyte. And I'm going to demonstrate how to do this in the next problem. So, which of these can be classified as weak electrolytes in an aqueous solution? To do this, we're going to apply this chart. In the first compound, we would ask, is it ionic or molecular? And in this case, it is going to be molecular. And we know that because there are no metals involved and there's not an ammonium ion. Now we're down here. We ask, is it an acid, base, or neither? We know it's an acid because it starts with an H. Then we want to know, is it a strong acid? This is on our list of strong acids, so this is a strong electrolyte. Okay? In the second case, is it ionic or molecular? There's no metals, so it's molecular. Is it acid, base, or neither? It's a base. It's an amine. And so this is a weak base. The third case, it's glucose. Is it ionic or molecular? It's molecular. No metals involved. Acid, base, or neither? There's no amines on it, and it's not an acid, so it's neither. It's a non-electrolyte. If you look at the structure of glucose, you'd see that it has alcohol groups, and so it's and those are the types of functional groups that are non-electrolytes. Barium hydroxide, is it ionic or molecular? In this case, we have a metal with a non-metal, and that means it's ionic. It's a strong electrolyte. This is one of the strong bases that you need to have memorized. Potassium nitride, is the compound ionic or molecular? Well, we have a metal with a non-metal, and so that makes it ionic. So this is a salt. The next one, we have ammonium bromide. And on initial look, you might think that this is molecular because it has no metals. However, you need to remember that ammonium is an exception, and it behaves as a metal because it's a cation, and so this is an ionic compound. It's a salt. HF, is it ionic or molecular? No metals involved, so it's molecular. And it's an acid because it starts with an H, and it's not one of our strong acids, therefore it's a weak electrolyte. Next one, H3PO4. This is molecular, no metals involved. It's an acid because we recognize that because it starts with an H, and it actually is one of our list of, or excuse me, it's not on our list of strong acid. It's a weak acid, weak electrolyte. Last compound, this is molecular. There's no metals involved and no ammonium. Acid, base, or neither. You might be tempted to think that it's a base because it has OH, but not all OH are bases. Many students make this mistake, so please be careful. It is neither. This is an alcohol group, and alcohol groups are non-electrolytes. That's it for this video. Thanks for watching. If you have questions, ask on Piazza and office hours or recitation. See you next time.